Hi class, I want to take this opportunity to talk about the data link and the network layer protocols. When we look at the data link layer, because of they manage access to the network medium, data link protocols also manage the transfer of datagrams across the network. Normally this means negotiating connections between two communication partners and transferring data between them. Such transfers are called point-to-point because they move from one interface to another on the same network segment or connection. When WAN protocols such as the PPP come into play, it's possible to use the following to establish links that carry IP and other datagrams from a sender to receiver: analog phone lines, digital technologies, which includes like ISDN or DSL and T-carrier connections, or switch technologies such as the X25 frame relay ATM. At the data link layer, this means that protocols must deliver services such as delimited bit level integrated checks, addressing for packet switch connections, and protocol identification for links that carry multiple types of protocols over a single connection. When we look at Ethernet 2 frames, their most common frame type on LANs, but a variety of other frame types exist that carry TCP IP over Ethernet networks. Other Ethernet frames types that can carry TCP IP include the Ethernet 802.2 LLC frames. Understanding frame layouts is critical for the proper handling of their contents, regardless of the type of frame in use. Such frame types typically include start markers or delimiters, sometimes called preambles, destination and source MAC layer addresses, type of field that identifies the protocol, the frame's payload, and the payload itself, which contains the actual data inside the frame. Most TCP/IP frame end with a trailer that stores the FCS field. It's used to provide a bit level integrity check for the frame's contents. By recalculating the special value called the CRC and comparing it to the value stored in the FCS field, the NIC can accept the frame for further processing or silently discard it with a discrepancy when the discrepancy occurs. At the lowest level of detail, it's important to understand the differences in the field layouts and the meaning when comparing various frame types for any particular network medium. You should understand these differences between the types of the Ethernet frames. Because hardware MAC layer addresses are so important when identifying individual hosts on any TCP/IP network segment, it's imperative to understand how the TCP/IP manages the translation between the MAC layer addresses and numeric IP addresses. For TCP/IP, the ARP provides this all-important role and helps create and manage the ARP cache, because ARP can check the validity of the address assigned to any machine by performing the ARP request for the machine's own address. ARP also can detect IP address duplications when it occurs in a single network segment. Understanding ARP packet fields greatly helps eliminate the address resolution process, particularly the use of the all zeros addresses in the target hardware address field to indicate that a value is needed. ARP also includes information about hardware type, protocol type, length of the hardware address, which is going to vary with the type of hardware, the length of the protocol address, and the opcode field that identifies what type of ARP or RARP packet is under scrutiny. A more advanced mechanism called proxy ARP permits a router to interconnect multiple network segments and make them behave like a single network segment. Because this means that hardware addresses are required for all segments that act like a single network segment. Proxy ARP's job is to forward ARP requests from one actual network segment to another when required and enable hardware address resolution, and then deliver corresponding replies to the original senders. Excuse me. Also, when the router configured for proxy ARP receives an ARP broadcast, it's going to respond with its own address. When it receives a subsequential data packet, it's going to forward it along and according to its routing tables. Network layer protocols then make the way into the data link layer through a process known as data encapsulation. Building the IP datagrams, therefore, depends on understanding how to map the contents of an IP packet into a datagram that's going to carry an IP packet and as its payload. This process requires obtaining a numeric IP address for the destination and may involve initial access to name resolution services such as DNS, and then using ARP or the ARP cache to map the destination address to the hardware address. It's possible to use a hardware address of a known router or default gateway instead, which then could begin the routing process from the sending network to the receiving network. When a frame must travel from one network segment to another to resolve its route must occur, local destinations can be reached with a single transfer at the data link layer. But when you look at the remote destinations, it's going to require forwarding and multiple hops to get to the sender, from the sender to the receiver. Thus, it's important to understand the role of the local routing tables that describe all the known local routes of a network, as well as the role of the default gateway that's going to handle the outbound traffic when exact routes are not known. So here ICMP comes into play to help manage the best route behavior and report when a destination may be unreachable or reachable. So let's look at the IP datagrams. Other important characteristics of the IP datagram is going to include the TTL, the time to live values, which prevent stale frames from persisting indefinitely on the network. Fragmentation of incoming frames when the next link on the router uses a smaller MTU than the incoming link. So reassembling of the fragments always occurs when the frame ultimately arrives at the destination host. And service delivery options to control packet and route priorities. Seldom used, but it's worth understanding. IP traffic can be prioritized by using the differential services or TOS destination. Although the TOS was defined in the original specification, current network prioritization implemented are based on the differential services function, which place a DSCP value in the IP header, and then this value is examined by routers along the path, and the traffic is forwarded according to the router configuration for the DSCP traffic type. In addition, then the ECN enables routers to notify each other of congested links before they must drop the packets. These services streamline the IP traffic to ensure that minimal delay for high priority traffic and a minimal packet losses. Routing protocols and routers provide a mechanism that can forward traffic from the sender's subnet to the intended receiver subnet. Generally, routers depend on access to tables of information that describe known routes and default routers, so the traffic can be directed within an internet worked environment, or the packets forward to other networks. Routers depend on the various routing protocols to manage the packet forwarding process. Interior routing protocols are designed to use within the autonomous routing domains, such as those that fall under the preview of and control of a single company or organization. Then you look at external routing protocols, and that's a means whereby the routers belonging to multiple companies or organizations can safely and securely forward data and manage routing information among the parties involved in a common connection. Looking at the distance vector routing protocols, which is like RIP, that represents the oldest and simplest type of routing protocol. There's a number of router transitions that are called hops that provide a crude metric of routing costs, and where no routing hops should occur as part of the routing topology. Link state routing protocols such as the OSPF are more sophisticated routing metrics and controls, and they not only can deal with multiple routes between the sender and receiver, but they have more powerful route metrics to balance load across the links or failover from less expensive to the more expensive routes as needed. OSPF then protocol supports routing structures that break up a network into routing areas. It helps to organize routing tables and behavior. In addition, then it's going to recognize special categories of routing areas, such as the backbone areas, where all the individual areas interconnected, and the AS, which represent the individual routing regions that fall under the specific administrative and management control. In such cases, the ABRs then may connect separate routing areas to the backbone or to other routing areas through the bridges. The routing characteristics, which determine how long it takes to route information and changes to stabilize within a group of routers that share information, help to determine what kind of routing protocols to use in specific applications. Important one is convergence, how long it takes for the routing protocol to calculate optimal routes following updates. It's going to include techniques such as split horizon, poison reverse, and the time to live settings. Other important characteristics include the information update mechanisms, whether broadcast or multicast, the router advertisements, and how the routing domains may logically subdivide to help manage complexity and reduce the router traffic. Managing routing on a complex network means that you understand how and when to use exterior and interior routing protocols, as well as how to establish the right kinds of connections between the multiple routing dimensions. Private WANs, links, the internet connections, and mobile users all require special handling when routing is concerned to make sure that the systems and services behave as required. It's important to understand how and when interior routing protocols such as the OSPF must interoperate with exterior routing protocols such as the BGM. The routing tables define the topology and behavior of the IP networks. It's instead essential to manage router security and updates as safely as possible. And for those reasons, storing passwords and secured links to access and update routers and their configurations is very essential. When you look at version 4 and version 6 of IP, they differ in a number of areas. When you look at IP4, it uses ARP to solicit layer link addresses. And if you look at IPv6, then it's using the network discovery process, the NDP. 4 is going to depend on routers to fragment packets into transfer links with different MTUs. But for 6, only the source node sets the size of the packets using the NDP discovery. And then 6 uses multicast rather than broadcast to send a single message to multiple nodes. The 6 nodes then listen for only those multicasts that are sent to their group or device type. The IP6 routing mechanism performs the same function as their 4 counterpoint to ensure that the packets successfully transfer different routing domains to arrive at the destinations. Mechanisms include how 6 routing decisions are made and weak or strong host behavior. 6 routers determine which route is in its routing table to make sure the forwarding decision by comparing bits in the prefix address for routing table entries to the same bits in the destination address. With that, then network nodes can be set to strong or weak host behavior depending on the traffic and the speed of the security concerns. When we look at the 6 MLDs, it's going to specify the multicast behavior as well as the MLD packets and message types. The MLD is the original protocol designed for IP6, and then there's the MLD version 2 update that's for the IGMP version 3. It's used by routers to discover multicast listeners on the direct connection links. Routers can both send queries and be the multicast listeners, and then the members of the multicast group can be located anywhere depending on the scope of their group. With it uses 3 message types. There's the query message, report message, and the done message. The IP version 6 routing protocols are RIP, the OSP version 3, the IGRP for IP version 6, and along with the MP, the BGP, and the EIGRP, and then of course the BGP. With that, the implications have changed a little for version 6. The multi-protocol EIGRP added the protocol-dependent module support for IP6, but it continues to operate as it's done under 4. The BGP added the multi-protocol extensions to allow it to operate with the 6 networks. Specific extensions are the next, hop, and the aggregator, and the NIRL. But other than those extensions, BGP works the same as it did under 4. Then RIP is based on RIP for IP4, but with the RIP-NG now uses IP6 for the transport and uses IP6 prefixes and next hop address. It also uses multicast group for all RIP updates, using the UDP. When you get to the OSPF version 3, for 6 it differs from 4 in that it's removed addressing semantics from its own packets and LSAs. It also runs on the pre-link basis rather than the per subnet, and generalizes its flooding scope and removes authentication from the protocol. I hope you found this information helpful as an overview of the 2 layers.